Merci Paul. Bonjour à tous
Thank you very
et
much, Paul.
bienvenue à
Good
cette
afternoon, everyone,
conférence
and
qui
welcome
porte
to
sur
this
la
conference that is
pyrogasification
focusing
pour
on
l'injection de
pyrogasification
gaz dans
for
les réseaux.
injection
C'est
into
une
gas
nouvelle
networks.
conférence sur la thématique
So
de
this is a
l'avenir et
new
celle des gaz
conference
verts.
on
Donc la
green gas,
pyrogasification, c'est une filière qui
and
permet de valoriser
pyrogasification
et
is a
réduire
sector
les
that makes
effluents
it
solides.
possible to
Et
optimize
aujourd'hui, on
solid
va comparer
residues, waste
à la fois
residues,
de cette
and we're
filière
going
en
to be
France
talking
et
about
également des
the sector in
démonstrations de
France and
production
also about
de
the
biomethane.
demonstrations that are up
Donc
and
cette
running,
conférence,
industrial
elle est
demonstrations of
s'articule
biomethane
en trois
production.
temps.
So the
Donc
conference is
tout
going to be
d'abord,
split
on
up
va
into
vous
three
présenter
parts.
le contexte
First of
et
all,
les
we'll
enjeux
present the
de la filière
context to you and
française
also the
de
challenges that the
pyrogasification
French
pour l'injection de
pyrogasification
gaz dans
sector
les réseaux.
faces for re-injecting
Donc je
gas
vais
into the network.
réaliser cette première partie
And
de la
I'm going to
présentation
provide
avec
this
mon
first
collègue
part of the
Bertrand.
presentation along with
Donc
my
moi, je
colleague
m'appelle Sandy
Bertrand Simon.
Sénéchal, je
My name is
travaille
Sandy
à
Seneschal.
GRT
I
Gaz
work
en tant que
specifically at
chef de
GRT Gas
projet sur la
as a project
pyrogasification.
manager for
Et je vais m'accompagner
pyrogasification
pour
specifically.
cette première
And
présentation
I'm
par
joined for this
Bertrand
first
Simon,
part by Bertrand
qui travaille
Simon,
également avec moi à
who
GRT
also
Gaz en
works
tant
with
que
me
directeur
at
de
GRT
projet
Gas
transition
as project
énergétique.
director for energy
Puis,
transition.
après vous avoir
Then
présenté le
slightly
contexte
further
de
down the
la
line, once
filière,
we've
on va se
presented
concentrer
the
sur deux
context for the
exemples de
sector, we're going to
démonstration de
focus on
production de
two
biométhane par les gaz dans les
demonstrations
réseaux.
for
Un premier exemple que je vous
injecting
présenterai un exemple au niveau européen avec le
biomethane.
projet du gaz en
And
Suède,
we'll first of all
qui est
look at a
actuellement en phase industrielle de
Swedish
production de
example.
gaz injecté
They
dans les
have
réseaux.
started producing gas and
Puis
injecting it
Marion
into the
Maheu,
network. And then
de
Marion
NG, chef
Mao
de
from
projet de
NG,
Gaia,
who's
vous
the head
présentera les
of the
succès
Gaia
de cette
Project, the R&D
plateforme
project, she'll talk about the
à Lyon.
success of their platform in Lyon.
Donc, ce qu'on vous propose, c'est de
So what
poser
we'd
vos
like to
questions
propose
au
is
fur
that
et à mesure
maybe
dans
you
le
could put your
chat
questions as time
et
goes
de
by on the
répondre à la
chat,
fin
and then
de
we'll answer
chaque
your questions
temps
at the
de
end of
présentation,
each
accompagné au
presentation,
fur et à mesure que vous le poserez.
hopefully being able to answer your questions gradually as the time goes by.
Donc, tout d'abord, le contexte et les
So
enjeux
first of
de la
all, the
filière
context and the
pyrogasification pour
challenges of the
l'injection dans les réseaux de gaz.
pyrogasification sector for injection into gas networks.
Bonjour Bertrand Simon.
Good
Alors,
afternoon, Bertrand Simon. Now,
est un
GRT gas
transporteur de
is
gaz en
a
France,
gas
aux côtés de Refrigal. Donc,
transporter,
nous
let's say
transportons le
in
gaz
France. We're in
sur
charge of
l'ensemble,
moving gas
sur 80% du
across
territoire.
80% of
Notre mission
France.
essentielle est finalement
Our
d'extraire le
our
gaz
main
qui
role
vient au pôle
is
conteneur
to
sous forme
take in the
gazeuse,
gas that arrives in a gaseous or liquid
par camion
format
méthanier, et puis de le
through
transporter sur
the
l'ensemble de la France
terminals, and
jusqu'aux
then
grands
afterwards we
industriels
transport the gas
importants
through to all
ou
of our
aux
major
centres de
industrial
consommation,
clients or to the main centres
notamment
as of which the gas
principales villes.
is
Nous avons,
consumed, in
nous
other words, the
opérons
major towns and
un
cities.
réseau de transport
We
de
run a
gaz
network,
de
a
plus de
gas
33 000
transport network
kilomètres
of
qui
about
répond sur le
33,000
coup aux
kilometres.
kilomètres de
So
voies
this
ferrées en
means
France,
that
pour vous
we
donner
cover as many
largement
kilometres as the
une
railways do
portée de
in
mesure.
France, just to give you an idea of how
Et
big our
on
network
transporte
is.
plus de
And
700
we
TWh
transport over
de gaz
500
par an,
terawatt hours of gas per year,
ce qui est
which
supérieur à
is
la consommation électrique
greater
française
than
par an.
the amount
Donc,
of electricity
une
consumed in
grande quantité
France each
d'énergie
year.
transite par la
So,
France.
as you can see, a great deal of energy
Les trois quarts en
travels
Grèce et les
through
tiers en
France,
France,
and the three quarters are used
avons
up in
remporté la
France,
partant
and about 20% of
dans
the
d'autres
energy
pays voisins.
then goes
Alors,
into neighboring
pourquoi
countries.
GRT Gaz
So,
ici? Eh
why
bien,
are
GRT Gaz
we
s'inscrit
talking about GRT gas here?
résolument dans
Well,
une
because
vision de
GRT
neutralité
gas
carbone en
is
2050.
decisively
Notre
involved in
vision,
achieving
c'est qu'en 2050, le
carbon
gaz pourrait
neutral,
passer
becoming carbon
dans
neutral by
notre réseau de
2050. We
transport,
consider that the gas that is
devrait être
part of our
décarboné
transport network has to be decarbonated,
en ligne avec les
and this has
objectifs
to be the case in line with the targets that have been set
que l'Europe s'est fixés.
for Europe.
Et pour ce faire,
Now, in order for this to be the case,
nous croyons résolument en la
we
capacité de la
also
France à
believe, and
produire
very
son
much so,
gaz
that
sur
France
son
has the capacity
territoire.
to produce its own
Et
gas
c'est la
on
raison pour
its
laquelle
French
on
territory.
s'investit
And this
pour
is
soutenir
why
les
we're
filières
investing heavily in order
de
to
production
support
de
the
gaz
different sectors
renouvelable
that
qui
are
développent.
gradually producing
La première
renewable
d'entre elles, c'est la
gas. One of the
méthanisation
first
qui a
sectors
déjà
is
pris son envol
methanization. This
et
has
qui est en
already
train de
taken
monter en
off, as we
puissance
say,
en
and is
France.
already ramping up its business activity in France.
Commence à produire des
It's
résultats
a sector that
tangibles.
is already beginning to produce some very
Cette
tangible
nouvelle
results.
révolution de gaz sera
This new
suivie
gas
par la
revolution will be followed
pyrogasification.
by
Il y a un potentiel
pyrogasification, we believe,
important en
that
matière de
also has a
production de
massive
gaz.
amount of potential when it
Et
comes to
puis
producing
enfin,
gas.
dans un troisième
And
temps,
last but not least, slightly
viendront
further
la
down the line,
gasification
we will
hydrocarbone
see
et l'hydrogène
gasification and hydrogen.
qui devrait pouvoir être
Gasification and
compléter le
hydrogen
dispositif.
that should round up this.
Voilà.
Donc avant de commencer à vous
So
parler de
Before we start talking to you about pyrogasification for injection in more detail, what we suggest is that we can introduce this conference by showing you a short video.
Pour réussir la transition énergétique,
In order to succeed with the energy transition, all of the different energy production sectors in the renewable sector have to become involved and come on board together. To reach this target, in order to favour the development of a circular economy, it is possible to convert many different residues into green energy and local energy on top of that that can be stored thanks to the gas infrastructures that exist. Thanks to pyrogasification, for example, we at GRT Gas, we believe that it is possible to optimise this waste that is produced locally and that has been very rarely used thanks to the traditional approaches, whether it's of renewable origin or not, such as residue from farming, for example, from the wine sector or from industrial sectors, or whether it's of non-renewable origin, such as plastics, furnishing waste, or packaging for foodstuffs. Well, all of this waste can potentially be used to produce green gas. Pyrogasification consists of basically heating materials that contain a great deal of carbon at a temperature between 850 and 1500 degrees centigrade. This operation aims mainly to decompose the raw material into different gaseous molecules. This mixture of molecules that we call syngas is mainly comprised of all different types of carbons. Methane is one of them, for example, and the molecules obtained are then recombined to produce a different type of gas. Once this gas is injected into the networks, it can be then used locally, and it can replace the natural gas that has up until now been provided. Local areas can potentially reduce by saying 50% the amount of waste that is then sent to tips, and 100% of the plastic recovered should be able to be recycled. This means that, potentially speaking, green gas production using injectable pyrogasification solutions would mean we can move from 75 to 140 terawatt hours. This accounts for approximately 1/3 of the gas present in the networks. By interconnecting the energies of the future, the transport network for GRT Gas will be the link between the resources available in the local areas that are as yet not used and the energies of tomorrow.
Alors après cette... Allô? Oui, je pense.
On t'entend, Bertrand.
Ouais,
We can
parfait.
hear you, Bertrand. That's fine. So following on from this short video that is rather didactic, at the end of the day, pyrogasification is a solution that responds to a certain number of challenges. Well, pyrogasification for injection in France is a solution to two challenges. The first challenge is that of processing our waste, the waste that we find in our local territories. And the second challenge, of course, is one of producing renewable gas energy, as I said earlier on. When it comes to the first challenge, Europe, and more specifically France, they currently face a situation whereby there is more and more waste piling up, and it's important to control and manage the waste, reduce the volumes, recycle it better, and use the ultimate residues in a much more efficient manner. So there is a legislative tool, a binding legislative tool in France that encourages us strongly to achieve all of these targets. I could refer, for example, to a certain number of bylaws in particular that focus on demanding the recycling of all of the plastics that we have in our society between now and 2025. And on exactly the same date, we will have the obligation also to divide by 2 the amount of residue that we send to landfills or that we bury underground every year. And this also is by 2025. So as you can see, these are targets that will be quite difficult to achieve, and all of the different regions in France have to comply with this exact same framework. So I would argue that yes, there is a major challenge out there for recycling our waste so that we can achieve these targets. It's important to note at this stage as well that a certain number of countries note notably China, for example, even they are starting more and more to close their doors to third-party countries that want them to import their waste that can come from the more developed countries, in other words. And as a result, this is also another aspect that is encouraging the Western countries to assume their responsibilities. Europe very recently produced a new set of rules and regulations as well that encourage the main European countries to cease from exporting certain types of waste, notably dangerous waste, hazardous waste, or non-recyclable waste beyond their borders. It's also important, I believe, to stress that pyrogasification for injection is part and parcel, it's resolutely part and parcel of the hierarchical framework for waste treatment and recycling. The aim is to recycle, of course, only the ultimate waste. In other words, the waste that has no other solution that is satisfactory in terms of reuse or in terms of recycling. So that's what I wanted to say for the first challenge. Concerning the second challenge, France also now has a whole set of rules and regulation that have to be abided by to guarantee that we reach carbon neutrality in 2050, as I said. And the first milestone is etched in stone in the law. It stipulates that in 2030, 10% of the consumption in France will have to be produced in a renewable manner, gas consumption. So this is the context for pyrogasification currently in France.
Une étude qui a été menée en
A study
2018
that was also carried out back in 2018, one that was coordinated by the ADEME, demonstrates that in 2050, 1/3 of the gas that will be used or consumed in France will be consumed thanks to pyrogasification. In other words, there's enough potential in our local territories for us to be able to guarantee that we can produce the gas that we need for our own consumption. So concretely speaking, how can we optimize residual waste? I'm afraid the speaker has two microphones functioning at the same time.
Parle pas, vous pouvez également couper leur micro afin d'éviter d'avoir un écho.
Sandy, excusez-moi, il y a un écho quand vous intervenez.
Sandy, I do apologize. There's an echo when you speak. Yes, sorry, I think I hadn't cut off certain microphones. Presumably this is better. Yeah, much better. Carry on. Okay, so how can we produce gas that can be injected into the networks starting from our waste? First of all, pyrogasification is designed for residual waste, solid waste that is either renewable or non-renewable. So basically, this waste is heated to a high temperature with little or no oxygen. So this is what creates the difference between pyrogasification and standard combustion systems. So we heat the waste up to a temperature of 700 to 1500 degrees centigrade. Then we decompose into syngas. This itself is partly made up of CH4, H2, CO, and also CO2.
Donc ce gaz de synthèse, il est ensuite épuré, donc nettoyé, puis on recombine ces molécules. Donc on recombine l'hydrogène avec le CO, l'hydrogène avec le CO2. C'est ce qu'on appelle la méthanation pour maximiser la production de CH4. Donc le CH4, c'est le méthane qui est ensuite injecté dans les réseaux de gaz. Donc la particularité de la production de gaz issus de pyrogasification pour injection dans les réseaux, c'est que cela permet de valoriser nos déchets en une énergie qui est non intermittente et qui est stockable. On s'affranchit ainsi des contraintes de saisonnalité car les réseaux de gaz permettent de transporter l'énergie plus tard pour qu'elle soit consommée plus tard et plus loin. Multiples usages possibles du gaz, donc ça peut être des usages mobilité, des usages pour la production de chaleur, d'électricité, ou également le gaz utilisé en tant que matière première dans l'industrie. Donc ce qu'il faut comprendre, c'est que sur l'ensemble de cette chaîne de production de gaz pour injection dans les réseaux, il existe des technologies matures sur chaque brique de la chaîne. Donc tout d'abord, la pyrogasification. Donc, les technologies de pyrogasification ont vu le jour dans le monde entier. Donc, on
So
recense
pyrogasification, over 150,000 to treat waste that can be either renewable or non-renewable. So it's a brick that is really quite mature. So the purification technology has been tried and tested at industrial scale, notably for treating gas, and it's also the case for methanation. So given that the entire chain is mature, we can conclude that the sector is ready to be industrialized in France. From a technical point of view, the challenge is really to find the best match for this technology in order to optimize the production of gas for it to be injected into the network. In terms of yield, so from the waste through to production and injection of the gas into the network, we're talking about energy yields that are really very high, between 70 and 80%, thanks to the use of the excess heat that is produced. And this sector, so gas for injection, is competitive as long as there's the right kind of support, like any kind of sector that's producing renewable energy. So as we were saying, pyrogasification is first of all a solution for reusing residual matter that cannot be recycled or reused. So we're talking about a broad range of reservoirs. We've identified 22 main categories that can be renewable materials, but also other types of materials. So forest waste, wood that's a little bit more polluted. So for example, wood that is polluted with solvents, for example, but also non-renewable waste such as old tires, plastic waste, or solid recovered fuel. So these are things that have been rejected from sorting units or things that come from our household waste. There are other, so these are the main categories that can be used in pyrogasification systems to produce a gas that can be re-injected into the network. So in Europe, there's a movement that has already been started for injection-based pyrogasification. There are different demonstrators that are emerging. We'll talk about the Gobi Gas project a little bit later on. You can also see, if you look at the graph on the right-hand side, that there's a European movement that's demonstrating the feasibility of the production of biomethane based on pyrogasification. So if you look at the light green parts of the graph, these are projects that are currently being set up. So you can see that in 2008, the movement had already begun. And in 2019, there were 2 projects that were being set up. And there are now 3 2 in France, 1 in England. But what we have to underline is that not only are we seeing new projects emerging, there are also projects that are achieving their objectives, producing a gas for re-injection. For example, Gobi Gas, that started to inject gas into the network in 2014. So there are different successful projects in Europe, and this means we have a solid base for commercial projects at European level, and in particular in France.
Bertrand, je te laisse la parole.
So Bertrand, if you'd like to take over to talk to us about the movement in France. Yeah, sorry, I hadn't activated my microphone. Yes, so talking about France, there's a great movement in France. Lots of things emerging, about 10 or so projects, pyrogasification for injections. And to those, there are a number of private projects that need to be added. So we don't have the details of those on this map. So all of these projects are projects that are part of a local circular economy. The aim is really to make the most of the local waste produced in the local area. And that's why most of them are supported by the local authorities. because they do provide a service. They treat the waste, but they also produce energy locally. Now let's focus on, among the projects, let's focus on 4 projects because GRT Gas is investing in these projects, it's supporting these projects. These are demonstrator projects, all 4 of them. So the aim behind the projects is to produce methane using a pyrogasification value chain or a methanation chain to produce different types of gas. So there's the ITIA project. It's a demonstrator, the synthane. The idea is to use pyrolysis that's very well controlled by ITIA with a the catalytic methanation process. There, the objective is to produce synthesized methane. So there's also one in the west, in Nantes. So it's the aim there is to couple a new kind of technology, a gasifier that is produced and controlled by lorry-works. And there's also a methanation unit, a biological methanation unit. This is innovative for Europe, and there will be a great future for this kind of process. And the further east we go, the Plaine de l'Ain, to the east of Lyon, there's a project called Pleine Énergie, bringing together different actors, different stakeholders, academics, authorities, industrialists, who have all come together in order to design and build a demonstrator to produce synthesized methane in order to use up local waste produced in the Plaine de l'Ain. And then finally, to finish this part on projects, there is Comitha. This is being supported by SICTUM and SIAP. These are associations that deal with household waste and wastewater. And this is in the Île-de-France area, so around Paris. So they've launched an innovation partnership. The idea is to co-methanize the organic part of the household waste and the wastewater sludge in order to produce a gas, and the digester, the solid part, will then be also used via methanation and pyrogasification units. So the digestate will not be returned to the soil because sometimes it's still polluted. And this is really the challenge of this innovation partnership. The idea being to develop the right kind of value stream.
La pyrogasification.
So pyrogasification for injection, as we see, we've got demonstrator projects, we've got commercial projects across France. It's a sector that is structured and very much mobilized. So there are over 50 stakeholders within the injection pyrogasification working group that's been working now for 5 years. The working group, it belongs to A2E, so that's an organization working on energy and the environment. So it works with different stakeholders. So within the working group, there are all of the different value stream stakeholders based on pyrogasification, waste stakeholders, and network operators and gas stakeholders, as well as OEMs, French OEMs, design offices, but also key opinion leaders at regional and national level. So this sector, as far as we see, has different assets, and that's why GRT Gas and the industry generally are interested in it. Well, first of all, what are the advantages? Well, it's the use of the waste that we've just seen. But what is noteworthy is that often it's waste that we don't know what to do with. So often it's waste that is usually buried in landfills. So pyrogasification allows us to stop burying this waste and transform it into a resource. It also means that we can use a lot of different types of residual matter. So we mustn't get this wrong. Pyrogasification is not a penknife that can adapt to everything. It has to be sized according to the type of waste that it has to treat. But in the world of pyrogasification, there's a variety of technologies that, and that means that we can work with different types of matter. So there are also economic challenges that can be taken into account. So it's a sector that allows us to create units with local jobs, because the stakes are local, the challenges are local, and these jobs require different levels of qualification. And that's to be appreciated, given public policies in different regions. In France, we're talking about units that are really sized for the area in which they are installed. The idea is not to create huge plants. The idea is to deal with the waste that is produced locally. So the idea is not to have these plants in the center of cities, but really to have them around the periphery. So again, this is a very good advantage as far as we can see. Finally, talking about environmental challenges, injection pyrogasification is a sector that allows us to really reduce greenhouse gas emissions. Sandy will present to you the mix, and we'll hear about Gaia as well. So it allows us to really reduce fine particle emissions. So injection pyrogasification means that we're not in the same conditions as other technologies. We've got the right conditions to not emit pollutants, either where there's very little oxygen, so it's not the same conditions in terms of combustion, and that's why there's a considerable reduction of fine particles and pollutants that might otherwise be emitted. From an energy point of view, as we said earlier on, we produce energy that can be stored. It's not intermittent. It can be used later on, further away, so it can be used for multiple purposes. And the idea is to produce gas locally. So to aim for energy sovereignty, to stop importing fossil products, and to create activity in France, therefore to help the economy. So these are the different advantages that we see in pyrogasification for injection, and we believe that it's a sector that has a lovely future in France.
Donc, en quelques
Okay, so some key figures. So pyrogasification for injection is promising. This sector in 2030 it will represent 1 terawatt-hours of gas injected into the network. This corresponds to 165,000 tons of waste a year. And from an environmental point of view, we'll be able to reduce our CO2 emissions by 165,000 tons per year. So it's ready to be industrialized. So as of 2023, we will be able to industrialize this sector. There will be pyrogasification for injection plants ready. The projects will be sized according to the regions. And when we say this, the average power in France is between 2 and 30 megawatt CH4s. This corresponds, for those who are familiar with incoming tonnage, this is like 5,000 to 100,000 tons coming in a year. So this means that local reservoirs, local sources of waste will be optimized. So concretely, GRT gas, with this very strong conviction, is supporting the sector. It's feeding into national thinking, regional thinking. It's helping to federate stakeholders. We're also supporting local projects, and we're providing help with innovation. So innovation, of course, is necessary to make this technology even more efficient. So we're really there to listen to what regions have to say or what project leaders have to say, and to help this kind of system emerge even further. So to conclude, just in a few words, pyrogasification for injection in networks is a solution for really optimizing waste and producing gas locally that can be then injected into the networks. It's a dynamic sector in France. This can be seen by the deployment of the different stakeholders in the sector, but also by the emergence of commercial projects and demonstrators across France. So I suggest now that we close this first part of the conference with some questions and answers. So we'll take 5 to 10 minutes. So please, use the chat to ask your questions.
Alors, je vois tout
So
d'abord.
I can see, first of all, that there's a question about the yield of pyrogasification without reusing the heat. So the yield, the efficiency of pyrogasification as such is 80%. So it varies according to the inputs that are being treated and the technology used, of course. So to be more specific, there's the Gaia project that we can take as an example. So there, the efficiency without using the heat, if we take into account the yield, the waste to production of methane yield based on pyrogasification, we're looking at an efficiency of 60%, and we're talking about the methanogenic yield or efficiency. So usually it's between 70 and 80%. So there's another question. With respect to the diversity of the inputs that can be optimized via pyrogasification. So biomass residue, forest biomass residue, that might be qualified as clean, or more polluted inputs like Class B wood or solid recovered fuel. So what percentage of this kind of waste can be injected into the system? Well, you started to answer this question, Bertrand. Perhaps you'd like to give some more details?
Sur le pourcentage des déchets.
So the percentage of complicated waste that can be injected into the system, what is that percentage? Tires, solid recovered fuel. Yes, well, generally, some units are actually dedicated. They deal specifically with this kind of waste. You can have units that deal just with solid recovered fuel or Class B wood. You can also have units that deal with a mix of both. In fact, for any given technology, the idea is really, well, depending on the inputs, depending on the waste, and depending on what you want to make, the idea is to choose the right matches from the point of view of technology and operating conditions. But basically, we have units that can deal with 100% of complicated waste, or a mix of different types of waste. So it really depends on the sizing of the unit with respect to the waste or the mix of waste that we want to treat.
Alors, il y a une question, est-ce que les volumes produits permettront
So
d'héberger
what about the volumes produced? Are they dedicated just to local needs or might they be transported? Well, the volumes produced can either be injected onto the transmission network or the distribution network. The solution chosen will undoubtedly be linked to the closeness of the network. So you choose the closest network. That's usually the way things work. And then there are, of course, solutions to make sure that the injected gas is then distributed either locally, or if there are no local needs, it can be transported further away. But it's usually the geographic characteristic that is the determining factor, whether it's distributed locally or transmitted at a greater distance. We have different questions about the energy sources used for the process. Where does the heat come from for pyrogasification? So what we have to see here is that, well, for the entire system, well, maybe I should go back to a diagram just to illustrate what I'm going to say. So here you've got the pyrogasification brick. So we're talking about 700 to 1500 degrees C. So there's a need for energy for feeding into this biogasification stage. So we need an activation energy. We need to activate the process with this energy. And then for the rest of the system, it's exothermic. So once the system is going, it will be self-maintained.
Peut-être ce qu'on peut préciser, Sandy.
Perhaps what we can specify, Sandy, if I may just say something, if that's okay. So Marion Maheu, so coming back to the isothermal question, we need to have high temperatures. So why is it exothermal? That's because we use, in the gasification, we produce a char. This char is itself used afterwards in the combustion side of the process. And it's by the char combustion that we have the heat necessary for gasification. So once we're up and running, it means that we've already got part of the heat. And we also recirculate part of the syngas that is produced. We burn it. And this also provides additional heat that we need to keep the reaction going. And as Sandy was saying, methanation is exothermal, and so we have excess heat. So to answer the question, I think there was a question about yield. So without heat, we're looking at 60 to 70% for the entire system. But once we've optimized the heat, we're going up to 85% of global efficiency for the entire system. Thank you very much for those details, Marion. Yes, we'll have the Gaia Project presentation that will give us more details along with the Gaia presentation. There's another question about optimizing biochar and other byproducts. Yes, there is thinking about this. There's an organization in France that's interested in it. There's companies like IKEA, AFNO Energy, just to name a few. These are companies that are thinking about working with academic partners for optimizing the use of this biochar. Because it's bio, it can have a virtuous use as an organic amendment for soil. It can use infiltration systems, purification systems. So it also provides energy. It's a renewable form of energy. So it can be used to manufacture energy. And so it can provide organic amendment, as we said, but as well as that, it can also act as a water retainer. So there are lots of different thoughts about how to capitalize on biochar. And some regulations in Europe are more advanced in this sector with respect to how to use it to its best advantage.
Après, il y a pas mal de questions. Je pense
So there are a
qu'on
lot of questions. Perhaps we should answer these questions in writing.
pour le reste des questions.
Perhaps we should answer the remaining questions in writing. Yeah, just perhaps one last question. This has come up again. It's about the different business models possible. It's true that there are two main business models that can be envisaged. Of course, these need to be worked on a case-by-case basis. It really depends on the technology being used. So there's a business model that focuses on renewable waste, so biomethane that's produced. So there's a framework in France. There's the energy climate law. Now this makes it possible to have experimental contracts set up with calls for project, and the modalities for these projects are to be thought about with the local authorities, with the support of innovative sectors working in the pyrogasification field. And there's another business model that focuses on non-renewable waste. So there's a kind of a fee that it acts as a driver. So some companies did not know what to do with their waste, and so this was a means of making the most of it. So what we suggest is that we answer the remaining questions in writing. So Bio360, this platform means that we can be contacted easily and answer other questions that you may have, or you can contact us by mail. You've got our contact details here on the screen.
Après cette première
So
partie,
after this first part about the context and the challenges of pyrogasification for injection into the gas networks, we want to move on to demonstrators for the production of biomethane based on pyrogasification. So first of all, we're going to talk to you about the Gas project, which has reached an industrial size for the production of biomethane that's injected into the network. So why talk specifically about Gas? Well, that's because Gas is a first project. It's the first project in Europe to have demonstrated the possibility of doing this, and also because with our teams in our research and innovation center at GRT Gas, with our lab and Gas, we carried out a lot of measurements in 2018 to try and understand the composition of the biomethane produced, and we want to share the main results with you.
Alors pour vous donner quelques éléments de
So
contexte,
just to give you a rough idea of a few contextual elements regarding GRT Gas, Gas is based in Sweden, and they've aimed to decarbonate the transport sector. It's important to note that as of 1980 in Sweden, they had buses and cars that drove around Gothenburg using gas-powered engines. And at the beginning of the 20th century, Sweden was asking itself questions as to the environmental issues, and there are high taxes on fossil fuels, notably on transport fuels. Hence, this very much favors the development of all of the different renewable gas sectors. Also, in Sweden, there's a massive amount of wood residue available, of course, given the forestry coverage. So the aim of the Gas demonstrator is to demonstrate the commercial potential of biomethane made using biomass from forest residue through gasification by reducing the greenhouse gas emissions thanks to the production of a biofuel, a clean biofuel. So the project has two separate phases. The first phase concerns the building of a demonstrator, a 20 megawatt demonstrator. So here we're talking, as you can see, about a 20 megawatt demonstrator, so one that is of an industrial size. This is a very specific feature of the Gobi Gas project. I would suggest that you keep this in mind. The project has been calculated right from the outset for high power outputs. In France, for example, as we've seen previously speaking, and also as the different projects that are underway prove, we tend to focus a lot more on smaller demonstrators, smaller projects for 2 to 30 megawatts. So within the scope of this project, the Gobi Gas project, the demonstrator has a size of 20 megawatts that corresponds to the valorization of 90,000 tons a year of entrants. So this initial phase was entered into very successfully because it made it possible to produce biomethane, top quality biomethane, in line with the specs from the gas network. So here we're talking about compliance with the specs that were set out by our gas networks. Purely and simply, it means that this biomethane is sufficiently good to be injected into our networks and to be able to be carried through our networks in exactly the same way as the current gas that we transport is. This is a project that accumulated 12,000 hours of operations globally speaking. That was for all of its operating process. So there's a first phase that was entered into successfully, as I said. The Gobi Gas project was structured in two phases, and the second phase focuses on the construction of the 100 megawatt unit in order to be able to demonstrate the profitability of the process from an economic perspective. It's important to note that this second phase was decided upon, but we decided not to announce it because we can receive operating support, but sometimes inappropriate operating support. And this was the case here. It's the additional money that was able to be made available. So at the time, we had a specific context that was slightly more complicated and unfavorable to the environment, a lot more so than it is now. So it meant that the prices of biogas were very different at the time. You might remember the COP21 where we were all quite disappointed at the objectives for reducing greenhouse effect gases. So basically, given that the targets were less ambitious, well, renewable gases were not seen to be important in Sweden and there wasn't enough money available. A second point to keep in mind is that locally speaking at the time, we had a territorial context whereby biogas in Sweden wasn't sufficiently competitive compared with the biogas produced by our neighbours in Denmark. So our support mechanisms weren't appropriate at the time because we wanted to be able to benefit from lower taxes. So basically, what I'm simply saying is you have to have an excellent support mechanism that is based on the development of the research work rather than basing it on the end result and taxing the end product. So in terms of this project, it's important to note that we have partners from all different sectors that came together. The first partner that we had for the project was Göteborg Energy. They're in charge of managing the city of Göteborg, and they take on board the gas that is injected into their network and manage it. Next, we have equipment providers such as Valmet and Jacobs Process for the methanation part. And we also had financial partners, notably Aon, that provided us with a grant. Just a few key dates that I'd like to give you. The Gobi Gas project came about in 2005. So from 2005 to 2009, we dedicated the work to the feasibility studies for the project. Then in 2010, a decision was made to invest money. This was notably from a 24 million euro investment that was provided by the Swedish Energy Agency. This, tangibly speaking, enabled us to start the building work. After 3 years, the gasification section work was completed. This meant that we were able to commission it and begin the first gasification processes. Then in 2014, only a year later, we had been able to demonstrate that we had biomethane that was injected into the network. Then after that, from 2015 to 2018, the project was up and running and functioned with wood pellets. I'll explain this a bit further down the line, but basically we accepted that the project could be commissioned to function with wood pellets, and we did a certain number of tests as well on other entrants. We tested them specifically for the Gobi Gas demonstrator project. At the end of the day, in February 2018, we were able to demonstrate that the Gobi Gas demonstrator had operated for 12,000 hours, and the unit was stopped in May 2018, nevertheless, because the demonstrator had achieved its targets in terms of the quality of the biomethane that was produced. And the second reason was that it was decided to not make the investments required for continuing on the project.
Alors, plus précisément sur la
Now, to be more precise on the question of the entrants, the Gobi Gas demonstrator recycles biomass type entrants, notably, for example, wood pellets from sawmills. For example, we were able to accept entrants that had been prepared in pellet shapes. We had 10,000 hours using byproducts sawmill. We had additional entrants that were tested, and they were tested for a variety of time frames. This enabled us to have syngas compositions based on the entrants that were used. We had, for example, we used wood chippings. These were wood chippings that originally came from residues from the forestry industry. They were chippings that couldn't be used in any way. The project also tested bark from paper pulp factory, and also Class A wood from wood pallets. The aim of the Gobi Gas demonstrator was to maximize the production of biomethane, and so to produce biomethane that could then be injected into the network for the fleet of vehicles that would travel thanks to the biomethane. So when it came to the demonstrator, we did manage to produce 60 gigawatt hours of methane. On this methane, we were then able to measure it very precisely and work out what it was comprised of. The aim was, of course, to have a clear vision of its composition, and then the results that we obtained, we were able to check the results with the European Standards Organization, and our methane-based product is perfectly compliant with the gas, for example, that is injected into the French network, so it could be used. Next, in terms of the technologies, we're talking about a pyrogasification technology and methanation processes that are used. The gasification process is provided by Valmex. This is a fluidized bed technology. It's a system that functions using steam. And in terms of the methanation technology, this was provided by Japa's process. This is methanation of a catalytic type. There have been a few questions around biological methanation. So there are two types of methanation. The first one is biological. And so in other words, it's a consortium, a biological consortium that digests, to simplify it, the syngas in order to be able to produce biomethane. Then there's another way of doing it. This is the method that we chose within the scope of the Gobi Gas project. That's to produce methane by using catalytic systems. You've got a catalyzer bed that basically speeds up the recombination of the molecules, the CO and the H2, so that you're able to maximize the reproduction of methane that is then injected into the network. Earlier on, we had a certain number of questions about the yield. Well, let me stress that the Gobi Gas project is illustrated notably taking into account the yield obtained from when the biomass is processed towards the production of the biomethane. So we're not taking into account the recuperation of any heat. And this methanogen yield within the scope of the project amounts to 63%. 63.
Alors concrètement, comment était réalisée
Tangibly speaking,
la gazéification
how did
pour le projet
we
Gobi Gas?
proceed with the gasification process with the Gobi Gas project? You've got the technical diagram on the right-hand side, but on the left-hand side, I'd simply like to say that it's a standard pyrogasification project for injecting gas into the network. There are 4 main stages. First of all, the gasification stage. Then after that, the purification of the syngas. Syngas is cleaned in order to methanate it afterwards. The aim, of course, is to make sure that we're not deactivating the catalyzer of the methanator. Then afterwards, we make sure that it's compliant with the specs. Let's now go back to the issues related to the energy specifically. Just to go into more detail on the production process for gas that was used within the scope of the Gobi Gas project, we introduced the fuel, as you've seen here, it's biomass, it's the raw material, into a fluidized bed, and then it is gasified with steam. We decompose the different molecules of the biomass so that we're able to produce a syngas that is made of CH4, CO, CO2, and H2. Then after that, the non-convertible part of the fuel that we call the char, as Marion explained earlier, that is then conveyed towards a combustion zone. And in the combustion zone, the char is burned in order to produce the heat that is necessary for the gasification process. That's why earlier I talked about the fluidized bed with water. That's because you've got the gasification part and then you've got another fluidized bed for the combustion part. And this is what generates the heat that is necessary for the process. And of course, the fumes, you have the fumes from the combustion part that are cleaned, and this means that in a standard manner, we're complying with the values and the fact that we're looking to limit the emissions. Next, in a second part, the syngas is then purified. Any tar is taken out of it, for example. This is done using standard technologies, those that are tried and tested for gas treatment. Then after that, prior to the methanation process, we adjust the carbon and the other product content so that we've got the right level of product for the methanation process. And then afterwards, the methane that is produced, it needs to be injected into our networks, and we dry it and we remove the residual CO2 so that we're then going to be able to inject the product into the network.
Alors, comme on vous le disait, le méthane
As we
produit,
said earlier, the methane that we produce, we've been able to prove that it is compliant. We've felt reassured thanks to the campaign that was carried out by NG Lab, GRT Gas, and Cregen and Gobi Gas. So we are in line with the European standards, so we know we can inject this gas into the network. The Gobi Gas project as such also has made it possible to provide a great deal of data about the composition of syngas that is made using different entrants, the entrants that I described. There are quite a few questions on this in the chat, so you've got the information in relation to the questions in this table. And concerning the environmental performance, I've seen questions on this. Well, in the Gobi Gas project, as I said, we used use the different types of wood, and this enabled us to reduce by 80 to 85% the greenhouse gas effect emissions. Hence, it means that we comply with the standards that have been set out at a European level by the European Directive for Renewable Energies. So at the time it was the RED directive, but now we have the new versions, RED 2, that are currently being translated into French law and into European law. Next, regarding the funding and the economic issues, The demonstrator was funded, as I said, for the most part by Göteborg Energy and its funds. That's the Swedish municipality organization. They also benefited from the Swedish Energy Agency's subsidies, 24 million, and also a financial partnership with E.ON. Next, in terms of the production costs, well, depending on the entrants, the production costs amounted to approximately 50 to 90 euros per megawatt hour.
Pour mettre en perspective ce projet,
Simply to give you a clear vision of the Gobi gas demonstrator, in terms of its performance, it is the first unit at an industrial scale to convert biomass into injectable biomethane that can be injected into the gas network. That's the gasification. Biomethane, as we've already said, this biomethane is top quality biomethane because it's compliant with the biomethane standards, the European standards, and also the project achieved its targets of demonstrating that it was possible to produce certain volumes using 20 megawatt hours. So in terms next of the technical performance, we had a certain number of success factors that we were focusing on. We wanted to achieve a good level of yield without taking into account the heat. We achieved 63%. And this demonstrator also enabled us to capitalize on a certain number of other types of feedback. Obviously, over time, we were able to solve a certain number of problems that we'd encountered previously. And hence, as a result, we now have a good set of foundations for future projects for pyrogasification, for future injection into the network. And last but not least, concerning the environmental performance, we also achieved good results in terms of reducing greenhouse gas emissions between 80 to 85%. This is according to the RED directive, as I said.
Alors pour conclure, en quelques mots
Just to
sur
conclude in a few words on Gobi gas, this is an industrial-sized demonstrator, as I said, of pyrogasification for injection of gas into the network. So we've said it's an industrial-sized demonstrators. When you look at the power generation, it's capable of producing up to 90,000 tons, capable of upgrading or valorizing up to 90,000 tons of wood each year. It produced biomethane, as I said, that was able to be re-injected into the network, and the biomethane that was produced was top quality biomethane in line with the biomethane standards, and that can be injected into the French networks.
On va essayer de résumer au maximum.
We're now going to be as brief as possible on what we say, and I'd like to just take a few minutes, roughly 5 minutes. We haven't got very much time left to answer any questions that you have. I've seen lots and lots of questions in the chat, so let's have a look.
Alors, j'essaie de remonter au tout début. Bertrand, si... Hop,
Bertrand, do feel free if you've been reading the questions, if you'd like to start answering them.
Alors, Jean-Marion, tu as répondu à une partie des questions.
Marion, I can see that you've answered some of the questions. Yes. We do have one question in relation to reducing greenhouse gas emissions. So here the question is related to the methodology to be used according to the European Union. We're talking about reducing the emissions in relation to fossil fuels. In relation to the production of natural gas.
Alors, on parlait de conflit d'usage.
We talked about conflict of use. This is in the chat in relation to wood. Let me just remind you that pyrogasification for injection, this is a solution that we use for all the different types of wood waste that can't be used otherwise. It's all the residues that cannot be recycled, that cannot be used as raw material in order to produce energy.
Il y a une question, pourquoi ne pas avoir
There's
continué
another question. Why did you not continue to run the demonstrator in order to be able to optimize the process and the system? Answer, well, it's true that I didn't really go into detail on that because it was all a bit technical. Let me try and find the right page. I'm not quite sure what the technical level is of all of the different participants. Let's just say that numerous optimization phases were entered into nevertheless. So I could talk in detail about them in terms of the process if you're interested. We do have quite a lot of feedback, whether it's a question of reducing as much as possible the amount of pollutants, also reducing the dwell time in the gasifier, optimizing the purification process. There are all kinds of ways in which we attempted to optimize the process, but it is true that the demonstrator reached its targets within the scope of the project. The basic aim of the demonstrator was simply to illustrate that we could produce a good quality product, technically speaking, that the biomethane that we could produce using biomass would be sufficiently efficient as energies go to inject into the network. So we achieved the targets. We achieved the 63% yield that we were looking to achieve and that we've already talked about. The demonstrator project in its initial phase wasn't designed to be profitable, and the demonstration of the economic profitability that formed the subject of the second phase. And as you can see, and as we saw, the decision was made not to launch this second phase, basically because we didn't have a sufficiently appropriate support network at the time, or support solution to provide us with the funding for this. Concerning the Capex, we're talking here about the demonstrator. Of course, it hasn't been optimized from an economic perspective. The Capex amounts to 125 million euros for this project.
Alors, pour les coûts de production,
for the production costs, the production costs are mentioned in euros for the number of megawatt hours of gas produced. So if it was the price of the intrant, it would have been very, very expensive.
Je vois que le temps défile. Je vous
So
propose
I can see that time is marching on. So I suggest that maybe we could move on to the next presentation. We've just seen a European project whereby we've seen the example of biomethane being injected into the network. We've also got another example, a great example in France. And Marion, let me pass the floor over to you so that you can now present the Gaia project.
Alors, est-ce que vous voyez mon écran?
Are you all able to see my screen?
C'est bon, Marion.
Ok, super.
Yeah, all good, Marion. Thank you. So good afternoon, everybody. My name is Marion Maheu, and I work at the Research Centre, the Corporate Energy Research Centre. And in particular, I'm in charge of the business activities doing research work on pyrogasification for the production of renewable gas. And in particular, I'm in charge of the R&D activities that revolve around the Gaia platform. Now, Sandy and Bertrand have already given you a very good overview and they've given you a good explanation as to how the sector functions, what the production chain looks like. So what I'm going to do now is home in on exactly what we do within the context of Gaia, show you the platform, and talk about the major results that we've been able to achieve over the last few months. So Very briefly, on the Gaia project, it's basically a collaborative project that came about 10 years ago. At the time, it brought together 11 partners, including NG. You've got the list of the different partners who've made their contribution in the bottom left-hand corner. All of these partners were able to provide their expertise on all of the production chain. The project is an ambitious project, and at the time, the aim was to demonstrate the feasibility from a technical, economic, and environmental perspective of producing biomethane, what we call second generation biomethane, and of gradually providing the necessary support so that it could be ramped up for industrialization in 2023. This was NG's major project, the aim being to industrialize, and this is still scheduled to begin in 2023. The project also received funding from the French ADEME and also labeling from Tenerdis Accélera and so on and so forth. One of the major challenges of this project was to demonstrate the feasibility at a scale that is a semi-industrial scale. So in the photo in the top right hand corner, you can see the Gaia platform. This was built in Saint-Fond, just above Lyon, by NG, and it is now operated and run by NG, by a department within NG. The Gaia platform is a unique platform, unique in Europe, even in the world. It's the only platform that is at a semi-industrial scale and that is up and running and that covers the whole range from the entrant, from the biomass to the waste, through to the actual production of biomethane or synmethane or synthesized methane. It is unique partly because it's an R&D platform. In other words, it's equipped with lots and lots of sensors, lots of wherewithal to perform analyses throughout the whole production chain. The basic target is to monitor absolutely everything that could potentially happen, the aim being to optimize its performance. Also, the site is a semi-industrial site because of its size, but also because we've made the decision, the conscious decision to build it and to run it in exactly the same way as we could run an industrial site. The result is that it's highly automated with a complete control room. Here, for example, in the top right-hand corner, you can see the operators in the control room. And since the tertiary, or from the tertiary building here, they're able to control all of the process area that is located here. And lastly, concerning the R&D aspects, we also have this capacity to be able to adapt and modify the platform. It really has been designed to be modular and flexible. So at the current time, there are certain technologies that are being tested, but we've got plenty of ideas for other innovative technologies, and there's still space to be able to test other technologies on the production line. So it really does have the vocation of performing R&D work, but its vocation is also to remove the risks and accelerate the industrialization phase and to share. Sharing is very important. We look to share our results, notably in order to be able to communicate with the local authorities, in order to demonstrate the performance of this sector and to illustrate that there is no risk from a set of different perspectives. So let me take you on a virtual visit around the platform.
Ici, une représentation schématique de la
So here
plateforme.
we have a diagram of the platform. So there's a first part here. This is the tertiary building. So in this building, we've got the control room that we can see here. And then there's the analysis laboratory. It's dedicated to the platform, but it's also the analysis laboratory for new gases, hydrogen, methane, syngas, etc., from the NG Research Center. You also have a technology zone, which is just here. And this zone has the receiving area, so that's where the inputs come in. There's an area for storage. You've got storage cubicles, and then there's the pre-treatment area. So that's where the inputs are prepared. And here, this is the core of the process. It's the that's where the thermochemical conversion takes place. So you've got the gas, you've got the gasification, the syngas cleaning, and then methanation with condensation and dehydration of the methane. And here there's a building for the utilities, like that's where the steam is produced. I'm sorry, but there is music and we can no longer hear the speaker. I'm sorry, with the music on for the video, we can no longer hear the speaker. The speaker's voice is being covered by the music.
La musique et votre voix se jouent ensemble. Donc, si vous avez possible... Ah, voilà.
The music has been stopped. You need to start again because the music covered everything that was being said. Okay, I'll start again. Thank you, Marion. So I'll try and speed up a little bit. So you've seen the pictures. So this is the lab, the analysis lab. You can see the equipment in the lab. So then here we arrive in the control room. So you can see the operators who are controlling, changing parameters, operating parameters remotely on equipment that is located in the technology area. This is the tertiary building that leads to the technology area. So you've got trucks that come in here, they unload the biomass and the waste. Then here in this part, you've got storage cubicles for the input. So whether we're talking about biomass or waste. Here you've got the pre-treatment preparation part of the process, removal of iron, screening, drying. And what we can't see very well over here, there are 3 hoppers for dosing and mixing up to 3 different types of inputs. And this big conveyor here takes the inputs up to the gasification stage. And in this part, you've got the thermochemical conversion skid. So you've got the gasification here, you've got the purification of the syngas part here. That's all part of the skid. We can't really see it very well. And here we've got the methanation part of the process. So there we go. So just to summarize the results obtained up until now, so the Gaia project is in fact a project that had 4 main objectives. So test technologies available on the market, so the gasifier, for example, and any similar gasifiers used for Gobi gas. Gobi gas was presented by Sandy just beforehand. And also to look into other innovative technologies patented by ENGIE. So we've filed for 10 patents, in fact, over the course of time. So one of the major challenges as well was not to use mature technology, ready technology, because we saw that the production costs were quite expensive. So thanks to innovations here at ENGIE, we were able to reduce things by 40 megawatt hours. So if I draw a parallel with Gobi gas, we changed the methanation brick an awful lot. I don't know if you remember the diagram shown by Sandy, but on that diagram, we could see that there was a large part that was occupied by methanation. And there were 4 to 5 reactors altogether for the water gas shift, 3 methanation reactors, but for Gaia, we've just got 1 reactor that does everything. And this means that we can save a lot in terms of space. And one of the other objectives was to develop tools to prepare for industrialization. So we can, in fact, deliver a kind of a micro process with the sizing, with all of the process documents required to start. We also aimed to carry out life cycle analyses because we're talking about renewable gas. So this was reviewed and criticized by a panel of external experts. And the major results from this concerned the base that was updated. So we had 64 grams per kilowatt hour of biomethane produced. And with the RED 2 methodology and with respect to a fossil fuel, a reference fossil fuel, we were able to reduce that by 80%. So in terms of major results for the platform, we demonstrated that we were able to produce biomethane using biomass. So our first cubic meters of biomethane were produced at the end of 2019. And we made a major step forward recently. So a year later, we were able to show that the process worked and it was integrated by NG. And we were able to show that we were able to treat solid recovered fuel. And in November last year, we made our first cubic meters. So this is just to say the same thing, basically. So with these tests that were carried out, we managed in a very little time to move from the biomass and the solid recovered fuel. We showed that the synthesized gas was robust. It was able to go through to methanation. And we also measured different components in the syngas, in the fumes, in the synthesized methane, to look at trace materials, look at organic components, sulfur, ammonia, etc. But also in the fumes, NOx, SOx, HCTs, COVs, and other components. So we were able to look into all of these things. And we were able to analyze the solid residue of the process. So from the point of view of industrialization, the Gaia project made it possible for NG to move on to industrialization. So currently, that's what we're doing. We're industrializing. The first commercial unit that will start to be built in 2023 will be based on the Gaia process. So we're planning to start operations in 2026. So the commercial demonstrator will be located in Le Havre in the port area, and it will have a size of 20 megawatts. So that's similar to what Sandy and Bertrand were referring to. And it will be fueled by wood waste or solid recovered fuel. Now to finish, the Gaia platform up until now has been dedicated to the conversion of biomass, the idea being to produce synthesized biomethane. Very recently, we've developed the platform further so that we can use waste. We're going to continue to broaden the type of waste that can be treated by this kind of process. The objective, of course, is to be able to work with very low cost waste, as negative a cost as possible, in order to have something that's very profitable. So we want the platform basically to be dedicated to the production of renewable gas by pyrogasification. So we want to be able to produce hydrogen, because according to the first research work carried out over the past few years in the lab, without making too many adaptations, we can produce hydrogen using a similar kind of system. So in the future, well, in fact, we're doing a lot of brainstorming at the moment, and we're setting up consortiums for new R&D projects focused on the platform. So if you're interested in contacting us, being part of this, contact us by mail. We also want to open up the platform to other project leaders who want to look into purification of syngas or synthesize methane or second generation methane. They can then test it as test the real gas. So we're open up to this kind of thing where we can allow other people to use it for testing purposes. Also, there's something else that we want to do. We want to be able to disseminate our results, to provide feedback to others so that the sector can develop further. So Sandy was talking about the club, the pyrogasification club. So this is part of it. The idea is to bring together experimental data arising from the platform. Are there any questions? Thank you very much, Marion. I see that there are many, many questions. So perhaps we can take 10 minutes for questions and answers and then conclude. So notably, there are questions about methanation, the technology developed by ENGIE for this. Okay, let me have a look. So which technology, is that the question? Yes, what methanation technology are you using? It's catalytic methanation technology with a fluidized bed. This makes it possible to be isothermal. In other words, we cool things down during the methanation reaction. So today, you have mainly fixed bed technologies. They're adiabatic, isothermic. So you increase the temperature using this kind of process, and as the reaction is not in the best condition, you then have to cool down it as an intermediate stage and go back to another methanation reactor. This is the case for the Gaia gas project, for example. Have you solved the problem of tar? Well, we haven't really, for the time being, encountered any problems with tar. So we've got a first stage for cooling down the syngas. So we condense the heaviest tar. And then part of the washing of the syngas allows us to capture a lot of heavy tar and some of the lighter tar, benzene, etc. And then we have adsorption columns that allow us to retrieve the last portions of light tar. So today we haven't had any specific problems linked to that. What uses for the Salamander project? So what we're planning for that project, I suppose you're talking about the use of syn methane, right? So what we're planning is an injection type of use, but we also want use for mobility. So something else was suggested. The sector makes it possible to produce quite a lot of heat. So there are inputs, but there's the process system. But for a 20 megawatt unit, we can produce between 6 and 10 megawatts of additional heat. So we're looking at what we can do with that heat, especially in the port sector, for example. And what about partners? I'm not directly involved in discussions with industrial partners because I'm more of an R&D sort of person. There's another team in charge of the industrial project, so I won't really be able to tell you about the partners chosen to date. So I can't really tell you whether they might be interested. Well, ammonia, there are traces of ammonia. What about the share of energy consumption for the overall environmental balance? What about electricity? So this is a very good question. I can't remember the exact percentage, the exact figure, but the consumption of electricity represents something like 20%, if my memory serves me right, of the overall environmental balance. So for the French context with electricity that's low carbon, we've got a reduction in greenhouse gas emissions. It's bigger than what you have on average in Europe. So the emissions factor, I can't remember what it is, but I can give it to you later. What about tests carried out on Class B wood? No, not yet. We haven't done any yet, but what we think is, well, it's like doing the splits between clean biomass and solid recovered fuel, because they're really quite the opposite in terms of quality. So Class B wood, we're not that worried because it's mainly going to be wood. We've been able to test biomass, but with more pollutants. So we've tested, the system with solid recovered fuel, because this is something that can be used, but we haven't really tested it fully. Do we use starting motors? No, we don't. I imagine that that's for the production. No, we don't use any starting motors. We don't look at the production of electricity very much. It's very specific to France, I suppose, because the carbon context in France means that there's no point optimizing the excess heat and converting the methane. It's better to convert the syngas directly into heat for gas engines. But if there was a European mix, perhaps that's something that would have to be thought about in order to reduce the self-consumption of electricity. Does it produce biochar that can be reused and optimized? As Sandy was saying, the Gaia technology, there are two compartments, if you like. There's a gasifier and a combustion system. So the char that's produced by pyrolysis, that's gasified in the pyrogasification part, is in the combustion system, and it's burnt in that system, and that's what provides the heat. So the solid residue that remains is mainly ash, but that ash can contain a little bit of char to a certain extent. But we look at how to optimize the ash more than anything. And coming back to the discussion earlier on, there are many ways to do this. Muck spreading, sending them to dangerous waste treatment centers. What is the level of pollutants? It really depends. What about a methanation technology? Are you familiar with, I think she said Metavag? So yes, we're familiar with this technology and developed by Terraga. It's more applicable. Well, this technology is advantageous for the gas sector because being able to have stop and go thanks to magnetic induction, this offers an advantage. Have you tried to use IMRs? I can't really answer that question because we're still carrying out our tests. We've carried out our first tests. We did them last year. What I can say is that the solid recovered fuels tested are what you can find on the French market, but I can't really give you any more information about them. Do you treat the fumes in a particular way? No, we don't. So just to add to what Bertrand was saying earlier on, in fact, we've got a post-combustion chamber. We've got a filter as well to filter the particles, so especially ash, a little bit of char. And we have something else, a mineral matter like sand. And we also have something else. In fact, we add certain additives in order to capture other inorganic components. And then at the end of the chain, we've got a torching chamber. So just to add to what Bertrand was saying, and coming back to the process we use, basically we reduce the volume of fumes by a factor of 10 because we've got direct combustion of the biomass or of the solid recovered fuel. So first of all, we reduce the initial input into a char, we gasify part of that char, and then there's another part of the char which will find itself in the combustion unit. And so the quantity of air required for the burning process is much lower than if you were burning the input directly. And so there are fewer vapors that are produced. So the treatment equipment is also smaller for the vapor. So we also save, if you like, in terms of cost for that part of the system. So I don't know if I've got much time left. I can see it's already 3:39. What about urban sludge inputs for Gaia? Well, that's a very good question. Yes, that could be part of the process. The question is more to have a pre-treatment for this sludge, or at least some kind of drying operation, because in gasification you need to have inputs that have humidity that is lower than 20%. Well, it's recommended, let's say, because otherwise you really reduce the energy efficiency of the whole installation. Keeping in mind that the drying is carried out at a low temperature, it's lower than 90 degrees, so it's not a heat that can be used. It's lost heat. Okay, thank you very much, Marion. Time is ticking on, and another conference is going to be starting soon. So thank you very much for taking part in this conference. So pyogasification for injection makes it possible to really optimize waste, what happens to waste. We can produce a gas locally that can be then injected into the network. It's a dynamic sector with several commercial projects and demonstrators that are seeing the light of day in France. And we've also seen the technical feasibility for the production of gas. This is what we've just seen with Marion's presentation, producing biomethane based on solid recovered fuel or biomass. And coming back to the gobi gas process with gas injection as well, based on pyrogasification and forest waste. So we're available. If you have any questions, if you would like to take an appointment, you can use the Bio360 platform or send us a mail. And if you would like to continue talking about pyrogasification, please join the conference on green gas for ATEE. where we'll be talking again about pyrogasification within the context of the Pyrogasification Club and the organization that is in charge of treating waste in the Île-de-France area. Thank you for your attention. Enjoy the rest of the day. Thank you very much.